Welcome to this video involving piecewise functions. We are going to discuss two problems in this video. The first is currently pictured on the screen. Given the algebraic representation of a function, can we sketch its graph? What we want and need to do is view the function one piece at a time. The first piece to the function is a line. The line would normally be written as y equals x plus 3. But this portion of the line we want is only the piece where x is less than or equal to negative 2. When we consider the line, the slope of that line is positive 1, the number attached to the x, and the y-intercept is 3. So when we go to sketch the graph, we want a line with a y-intercept of 3 and a slope of 1. So we will sketch some axes on our coordinate plane. For now, let's just have them centered. Label our x-axis, label our y-axis, and now let's plot the points for the line. The line has a y-intercept of 3, so it would start up 3, and its slope is positive 1, so it would go right 1, up 1, or it would go left 1, down 1 when plotting the points for that line. Now when we draw the line, we only want the portion of the line where the domain is such that x is less than or equal to negative 2. Hence, we only want the portion of the line that will be drawn in the highlighted region. So we will start at the point there, draw it down like so. Since this domain goes forever, we will put an arrow at the end of the line, and it has the or equal to option, so we do want that point to be filled in, or we want a solid point on the graph. Now let's get rid of the other portions of the graph that don't matter, the highlighted region as well as these other miscellaneous points. Next, let's consider the portion of the graph that goes from x being between negative 2 and positive 1. In that region, the graph that we will be looking at is a parabola. The parabola has its vertex at the point negative 1, comma, positive 2. That parabola is opening down because of the negative out front, and we don't have any multiplier with it. What we will notice is that we only want the portion of that parabola where x is greater than negative 2 but less than 1. So our vertex is at negative 1, positive 2. Let's put that point on the graph. A parabola is going to go over 1, down 1 to both the left and the right hand side. And then only to the right hand side, because of where we're drawing this parabola, we will go over 2 and down 4. Notice that that will be an open dot because at x equals 1, it's not specifically in the domain or on that piece of the graph for our parabola. So we will draw in our parabola, and there it is. Once we're done drawing the parabola, let's get rid of this highlighted region. That was just there to help us draw the graph. So now we have a third and final piece to this piecewise function. Anytime we just have a number as f of x equals negative 2, that's going to be a horizontal line. The normal way that we would have written the equation for that line is y equals negative 2. But we only want the piece of that horizontal line where x is greater than or equal to 1. So we go to where y equals negative 2, where x equals 1. We fill in the point that was already there. And now we're just going to have a horizontal line at the y value of negative 2. So we will draw in our horizontal line at the y value of negative 2. It goes forever because x is greater than or equal to 1. And once we've done that, we will get rid of this shaded, highlighted portion. What remains on our grid would be the graph of the given piecewise function. So that's how we sketch a piecewise function. Take it one piece at a time and just draw the portion of the graph that we care about. Now let's change it up. What if we were given the graph of the piecewise function and needed to write how the function would look in its algebraic notation. Again, we will just go one piece at a time. Let's start on the left-hand side. That first piece that we just highlighted in blue, that first piece is a line. We can quickly tell what the slope of that line is. Notice the line goes up 3 and over 1. Hence, the slope of that line is a positive 3. Unfortunately, we don't have the y-intercept readily visible on this graph. So in order to determine the y-intercept, we know the slope of the line is 3. Let's take a point on that line. For instance, negative 3, 4. Given the point and the slope, we can plug into y equals mx plus b to solve for the b. So we get 4 is equal to a positive 3 for the slope times a negative 3 plus b. So 4 is equal to a negative 9 plus b. Add 9 to both sides and we get that b is equal to 13. So the equation of our line with a slope of 3 and a y-intercept of 13 would be y equals 3x plus 13. So in the algebraic expression for our piecewise function, we will write this first piece, 3x plus 13. We put a comma then to designate what the domain of this piece of the graph would be. Notice it goes all the way to negative infinity, so x is going to be less than something, and x is specifically going to be less than negative 3. Let's put the or equal to option on that piece. Okay, now we're going to have another piece to this graph. The piece that we've just highlighted is a parabola. So this second item is a parabola. When we go to write the equation of the parabola, we find its vertex. This vertex is chilling at negative 1, 0. It's going upwards, and it doesn't have a multiple. So the parabola would normally have an equation of y equals x plus 1, the quantity squared, plus 0, but let's keep it simplified. Let's not put a plus 0 in the form of the equation. There's the parabola. Let's put it in our piecewise function. F of x equals x plus 1, the quantity squared. The x values for that parabola go between a negative 3 and a positive 1. Those are where the x values are at. So we'll say negative 3 is less than x is less than 1. We cannot double dip on the or equal to option. We've already used the or equals with negative 3. We cannot use it again here. Now, if we had originally put the first piece as a strict inequality, meaning x is strictly less than negative 3, we could have placed an or equal to option on this piece. It really doesn't matter. We can put it on either place, but only one of the two places. We can't put it on both. And now, the final piece of this function has been highlighted. It's a square root. The square root of the function there with the square root has its starting point or its center point at 1, 4. That square root is going down and to the right. There's no multiple. It goes over 1, down 1, over 4, down 2. Square root of 1 is 1, square root of 4 is 2. So this square root will be y equals negative, because going downward, square root of x minus 1 plus 4. Let's put that piece in our piecewise function. Negative square root of x minus 1 plus 4. That square root is going from positive 1 to infinity. So x is greater than 1. But notice if we just left it x is greater than 1, we haven't used the or equal to option, and there is a solid point on the graph at x equals 1. So in one of those two locations, we will have to put the or equal to option. It doesn't matter which one. So let's put it on the final piece of the piecewise function. It doesn't matter the order in which we write those pieces in the function itself. What matters is that we have each piece's algebra along with its corresponding domain. And if we keep this in mind, we should be able to work with piecewise functions.